Second Ben of the day is up next. Ben Greenhagan is going to talk about ground truthing laboratory experiments with diviner Lunar radiometer observation.
Great. Thanks a lot. Yeah, usually at these meetings I'm asked to use my soothing monotone and squiggly lines to kind of take it down from an LROC presentation, but this is going to be even more challenging, I think. All right, so yes, today I'm going to talk about some of the work we've been doing trying to tie the remote sensing observations from orbit to laboratory experiments, and that's using the diviner lunar radiometer and some specialized lab equipment. So this is a very busy backup slide, but I just wanted to kind of lay out the problem that we're dealing with here, and that's when you have a airless body like the moon, you have a very fine particulate surface, and it's being illuminated by the sun, and this creates a condition that's very different than you would see on Earth and Mars. So on Earth and Mars, you might have a situation like this plot up here in the upper left, where you would have your top particle, and you can go down in depth to millimeters, centimeters, and everything's basically going to be the same temperature. But on the moon, because of the vacuum environment, those top particles are significantly colder than the particles at depth. And the effect of this is very extreme in the mid-infrared, in the thermal infrared. And so our plot here on the right is showing for a mineral sample the difference between these two environments. The blue line would be that Earth, terrestrial, Mars-like environment, and then the black line would be if you go to an airless body. And you can see there's large changes in the spectral contrast, and this peak, the Christiansen feature peak, shifts to shorter wavelengths and becomes more pronounced. So we realized this using the literature before Diviner was launched, when it was in formulation. And so we designed Diviner to characterize the position of this emissivity maximum. It correlates with mineralogy, especially on a planet like, a body like the moon, which has such a limited range of mineralogy. And so we can use that to pull out what the composition of the moon is. Now, the motivation for bringing this up again is actually something that we presented at the Lunar Planetary Science Conference a number of years ago. And that was the correlation between this spectral feature, the Christiansen feature on the x-axis. I don't think I'm going to be able to do that. It correlates very well with iron, which is on the y-axis. So if you look at the plot on the left here. And this has been used by Carl Allen and others on the team to identify kind of an independent measure of iron using the diviner data. But back when we presented this, on the right-hand side was what the lab perspective was. And here you could see the data is kind of all over the place. And we were attributing this to different lab setups, since most of this was from literature, including data that had been collected back in the 1970s. And so in the intervening time, we've really been working on trying to establish the best possible lab practices that we can. We've expanded our collection of materials that we've been looking at, and we've been revising our methodology. So this is Diviner, the most photogenic instrument on Lunar Reconnaissance Orbiter. It has spectral channels at solar wavelengths, and then also in the mid-infrared from 8 microns all the way out to the far infrared, about 400 microns. And for the purposes of this study, we're really focusing on the 3 channels near 8 microns for the most part. The lab setup that we used for this is Pascal, which is a simulated airless body chamber at University of Oxford. And this was specifically designed, it's kind of a second or third generation one of these chambers at University of Oxford, to recreate lunar or asteroid-like conditions. And so it's a vacuum chamber. It has a liquid nitrogen-cooled shroud around the samples. The samples can be heated by conduction or illumination. Illumination is really important. And it's connected to an FTIR spectrometer, so we get hyperspectral measurements of the sample. And Pascal is not unique. There's a number of these chambers that have kind of cropped up over the past decade or so. The original University of Oxford chamber, SLEC, Simulated Lunar Environment Chamber, Sable at APL, which I manage, Parsec at Stony Brook, and ALEC at Brown, all have similar capabilities. But one of the things that we knew was happening, but we hadn't really appreciated until the past couple of years, was that the illumination on the sample is not normal, and it's not even a small illumination angle. It's actually off to the side at about 52 degrees. And so we wanted to reevaluate our methodology, where we were basically heating these samples up to kind of local noon-like temperatures, when in fact it's actually being illuminated from a more grazing angle. And so what would the effects be of heating to temperatures associated with that type of illumination? So if we take a look at what Diviner sees, on the left here, this would be a diurnal plot. So this would be daytime, 6 a.m. to 6 p.m. And you can see the peak. Would be for the Apollo 11 landing site, which would correspond with Apollo soil 10084. And you can see the kind of data density we have. On the right, this is now a temperature as a function of incidence angle. And the areas I've circled there are the range of incidence angles at these different setups. So each of these instruments has kind of a unique illumination geometry, with SLEC and ALEC having the most normal incidence angles, and then Pascal and Parsec having kind of the least normal incidence angles. And so that's the range of temperatures. So these are temperature differences of about 50 K, which is quite high. This is just an eye chart to show you the Apollo soils that we evaluated in the study. We have soils from all of the missions, and in particular, we were trying to use soils which were the reference soils, the top surface soils, and then did the calculations for what the measured temperatures were using the Diviner data at a range of different wavelengths. So not just at 8 microns, but also for some of Diviner's longer wavelength channels. All right, and then collected the data. Actually, Carrie Donaldson-Hanna collected most of this data for all of our entire suite of soils. And the plot on the left here is showing what these differences are between the incidence of 52 degrees estimated temperatures, and if we heat it to a noontime temperature. And it might not look like a whole lot on this plot. It's about 10 to 15 wave number. That's about 0.1 micron. But that's actually a pretty significant amount of shift compared to the shifts we see due just to the silicate composition. All right, so if we take a look at an example region, this is Apollo 16 with a selection of different sampling stations for which we had soils. Station 11 on the top, Station 1 in the middle, and Station 6 on the bottom. These would be the laboratory, the hyperspectral laboratory data, which have been put through the Diviner processing pipeline to pull out these types of spectra, and with the location of the Kristianstad feature listed there. Then the plot on the right would be a Diviner channel number plot. And I'll explain that in just a minute. If we bring in the Diviner data, we see we actually get a really nice match for both Apollo 11, a very immature site, Station 11, immature site, and Station 6, which is a more mature site. The match isn't quite as good at Station 1, and of course this could be due to maybe that sample wasn't particularly representative of that area, or maybe that area had a little extra roughness in it. So that's not completely unexpected. But 2 out of 3 is pretty good for this. Then those channel number plots I was talking about, here you can see the black lines. They start to deviate as you go to higher channel numbers, channels 6 and 7. And these are some of Diviner's far infrared channels. And the effect that we're seeing there is almost certainly due to anisothermality within the scene. So when you have rocks and soils together, or you have surface roughness, you'll start to get these differences at these longer wavelengths. All right, so we did the same thing for Apollo 15, Apollo 17, each of the sampling stations for which we had soils, and then we also did a single soil for Apollo 11, 12, and 14. And so I'm bringing back the plot that I showed here at the beginning. I should have mentioned this trend line. That's the linear fit to the Diviner trend that was described in Carl Allen's 2012 paper. So did we actually do any better doing this? And the answer was yes. Now there's a shift off of that Diviner trend, which is to be expected because that was based on data that was at noontime. So when we do this fit to the data that's at an instance angle of 52 degrees, we do shift to shorter wavelengths, and that shift is about 0.1 microns like we'd expect. Now, when I showed this initial result at LPSC, not quite as much data as we have here, it was pointed out that, well, you have all these points that are off the trend. And that was kind of bothering us because it's falling off the trend. So what could be going on here? Well, went back and looked to see what those soils actually were, and these are all high titanium basalts. Now, titanium has a couple effects on the CF. Ilmenite itself is dark. When you make things darker, it tends to reduce the spectral contrast and shift the features to longer wavelengths. which would be exactly what we're seeing here. The CF has shifted to longer wavelengths. That's why it's moving to the right. Ilmenite itself actually has a peak that's off closer to 13 microns than the 8 micron channels that we're looking at. So if we instead plot this function on the right here for our lab data versus iron plus titanium, we once again have this really nice trend. So this is starting to point to kind of a underappreciated dependency in the diviner data. And if we look at the diviner data on the left, now also taking titanium into account, we start to see that our linear approximation that we had for iron versus CF is breaking down, especially as you get to these high titanium basalts. So that's something we need to take another look at. We do fortunately have lots of different ways we can separate high and low titanium units, either using the diviner data set and a spectral index called the concavity index. We typically use this for looking at highly silicic regions, but it's also sensitive to areas that have high titanium basalts, or using some of the other data sets such as the Clementine or LRock titanium maps. All right. So that's pretty much what I want to say. So the title of this was using the diviner data to ground truth our laboratory experiment. I feel like we've gotten to that point now. So now the next step that we want to do is actually go back and recalculate the plot here on the left here, not using the noontime data, but specifically pulling out this instance, this higher incidence angle data to see if that better fits our trend. And then there's this question in the back of our mind, what's the effect of surface roughness? We know it's a huge effect in the diviner data itself, but our lab experiment doesn't have surface roughness. At the thermal scales that we would be looking at, which would be millimeters to centimeters scale roughness, the lab samples have none of that. And so what is the effect of not having that? And do we need to do lab experiments where we actually try to recreate that type of surface roughness? So that's all I have. I'll take any questions.
Time for questions?
One unique feature of the Apollo 17 site, of course, is that there's 5 to 20% pyroclastic ash in the material, and much of that ash are maybe beads, tiny beads. When I was looking at the pristine samples at Shorty Crater, you got a very high return at zero phase. I'm wondering if that might be affecting your data for 17 as well as the titanium issue.
Yeah, and that's an interesting idea, because one of the things we have learned is that the albedo and what the phase angle response would be does have an effect in the mid-infrared, and that was underappreciated before the mission. So that's a good point. And in Carl Allen's paper, he actually used the Torolithro pyroclastic site diviner data plus the geochemistry data from those glasses to kind of extend those plots to higher iron abundances as well, too. So, and they did fall on the trend.
Hi, Melissa Lane from Fibernetics. I have a question about trying to create the roughness for your laboratory measurements. It seems, I know it's not easy, but wouldn't it be a simpler solution just to try to change your laboratory setup to illuminate at zero phase?
Well, illuminating at zero phase would be really hard, just because we need a big mirror to get the energy into the spectrometer. About as smallest angle that we can do is about 30 degrees.
That's the smallest you can do?
Yeah.
Okay.
But regarding the surface roughness, the thermal modeling that's been done on the diviner team does show that even at these pretty small scales, you can have 30, 40 degree Kelvin differences in temperature at millimeter and centimeter scales with roughness.
And you just got right to my question. We are looking at diviner data at different, let's call it different times of day and evening, and looking at differential cooling and differential heating. Are you doing anything like that to, let's say, you have the light on, then you turn it off, and then you look at the differential cooling rates, and then you turn the light on and look at differential heating rates?
Yeah, actually, there was some really interesting data that we took with diviner of lunar eclipses, where you do get the closest you can to turning the light off and turning it back on. And so we did some laboratory experiments, and Carrie, we need to write this up. You get when you turn the light off, things basically follow thermophysics, and it's basically like you would find at the end of the day. But the really interesting thing was when the light turns back on, that the longer wavelengths heat up faster. And this actually corresponds to what the modeling suggests, is that those longer wavelengths are actually sensing maybe 2 particles deep, maybe 50 microns deep, whereas at 8 microns, we might be sensing 10 particles deep, maybe 200 microns deep. So you're getting the sense of differential heating as a function of wavelength, too.
Yeah, well, one of the things we're doing is look at differential densities, because obviously we're looking for metal fines and metal and things like that. So, and obviously the Apollo samples are too small to do that, but do you see any, it'd be really interesting to see your published data on differential heating and cooling. I think it would be a great contribution.
Okay, we'll chat offline.